Hello friends, as we know that computer science is a branch of engineering which uses algorithms for efficiently use real life problems and solve them so that it can be easily done as well as efficiently and in cost effective manner, in time effective manner, and all means basic rules should be followed. Let us discuss one example, that is nearest neighbor problem. For example, we are having some patients who require to go to their nearest hospital. Then how will they will locate that which hospital is nearest to them? Let us start. If we are given a service area and we have to locate the nearest hospital, then the blue points are showing the hospitals, and this particular Q point is a particular patient which requires to know that which hospital among these is the nearest one. So, in terms of the algorithm, what we require to input a set of points, that is site points, and to output a partitioning of the plane into regions of equal nearest neighbors so that every hospital can lie between this particular plane. We'll use the concept of Voronoi diagrams to illustrate this. Voronoi diagram is a concept which is very much used in the nature. That is, we can see the honeycomb, we can see constant soap bubbles, giraffe pigmentations, dragonfly wing, and in 1644, René Descartes, a scientist, used the influence of the stars by gravitation using this diagram. He has used informally, but in 1850, Dirichlet used 2D and 3D Voronoi diagrams in his study of quadratic forms. In 1854, British physician John Snow used a Voronoi diagram to illustrate how the majority of people who have been died in particular Shoho cholera epidemic lived closer to infected Broad Street pump than to any other water pump. So, for the spatial distribution of data. In 1908, Voronoi diagrams are named after Russian mathematician Georgy Fedosovich Voronoi, who defined and studied the general n-dimensional case. Voronoi diagrams are used in geophysics and meteorology to analyze spatial distribution of data. Now, this will be the resultant diagram, which will have dividing edges and some vertices. And how we'll make this diagram? Let us see the definition. Let P be a set of n distinct points, that is sides in a plane. The Voronoi diagram of P will be the subdivision of the plane into n cells, one for each side. For the point of view of patient, that is the point Q lies in the cell corresponding to a side Pi, element of capital P, if and only if Euclidean distance, that is normal scale distance between Q and Pi, should be less than to the Euclidean distance between Q and Pj for each distinct element, where Pi and Pj are the element of P. We can give another definition, that is 2 points Pi and Pj, which are the element of set of points. Let H, Pi, Pj denote the half plane containing Pi. So the Voronoi polygon associated with Pi can be defined as intersection of all the points I and j which are distinguished having the hyperplanes as means combined and resulting in the Voronoi polygon. Voronoi diagram can be constructed by this particular scene. If there is a single hospital, then this whole area will be the service area for this. And if we are having two hospitals, then what will happen? We'll have to divide their area of service like this. This line will go infinitely to both ways, and the patients of this area and the patients of this area will be the patients of these two particular hospitals. So we can illustrate for 2-point Voronoi diagram is a line that extends infinitely in both directions and two half planes on either sides. If we have series of collinear sides, then will result in series of parallel lines. When non-collinear sides will be existent, then these two bisectors will be meeting at a point from where again we can have another edge which is going to be half infinite edge, because these three edges are the half infinite edge because they are concentrating on this particular point, that is V, the vertex. So these can be known as half lines. And very interesting fact that these three sides are co-circular, and this particular vertex is the center of this circle. So we can define a Voronoi vertex is the center of an empty circle touching three sides. Therefore, the degree of V will be 3. Now, if we have 4 sides, then these 4 sides will be resulting in this particular diagram and resulting in a bounded cell and unbounded cell as shown. And this segment will be the bounded edge, these 3 segments will be the unbounded edge and half lines. There is another degenerate case when 4 or more points are co-circular. In that case, this can be very hard to design a diagram, because after that it will get complex. So we require to stick to not going for the more than 3 points. How this edge will be constructed? Let us see the summary. If this point is a cube, then there are so many points on this edge which are going to be co-circular with this particular 2 sides. There will be infinite many circles can be drawn using these 2 sides, and this particular edge will be the resultant of locus of that point. So a Voronoi edge can be defined as a subset of locus of points equidistant from Pi and Pj. You can also say a point Q lies on a Voronoi edge between sides Pi and Pj if and only if the largest empty circle centered at Q touches only Pi and Pj. Another point is that a Voronoi vertex will be a resultant of this circle center. That is, if these 3 sides are co-circular, then this particular point will be the Voronoi vertex. So we can illustrate that a Voronoi vertex is an intersection of 3 segments, each equidistant from a pair of sides. There is another intuition that not all bisectors are Voronoi edges. That is, the nearest neighbors can draw only the edges, not the far aparts. As in this particular example, we see that these 2 red points or red sides are not the part of this particular edge, because this edge is not the Voronoi edge. Why? Because they are far apart. There is another construction example. Will again result in a bounded cell. We can repeat this for each side, and having the running time big O of n square log n. Again, there is another divide and conquer strategy which can result in a Voronoi diagram. Let us see. Inputs for this particular approach is a set S of n planar points. Output will be the Voronoi diagram. Step 1, if S is less than of 4 points, then we can directly return the result. In step 2, we can find the median line perpendicular to the x-axis which divides S into SL and SR, that is left and right. In step 3, we can do this particular process recursively and resulting in a Voronoi diagram of left and Voronoi diagram of right. In step 4, we can construct the dividing piecewise linear hyperplanes, and simultaneously we can result in final resulting Voronoi diagram. Let us see an intermediate situation. For example, these two diagrams have to be merged in the last step. Then what will happen? We'll take the perpendicular bisector of P6 and P9. These are the nearest neighbors again, P6 and P8, P7 and P8, P7 and P11, P5 and P11, so on. So these edges are the bisectors of these two points. Again, P6 and P8 are having this particular bisector. There is another bisector between P7 and P8. There is another one between P7 and P11. There is another bisector here between P5 and P11. After merging, we'll remove these extra edges which are outside the another diagram. So the resulting diagram will be looking like this. The characteristic can be discussed, which has been discussed earlier also. Collinear points will result in these parallel lines. There is another theorem which can show the use that Voronoi diagram of P consists of n minus 1 parallel lines and n cells, otherwise it will be a connected graph and its edges are either line segments or half lines. Each Voronoi vertex should have the degree 3. The circle through the 3 points define a vertex of the Voronoi diagram and it does not contain any other point. Again, the locus of center of a largest empty circle passing through only a pair of points Pi, Pj defines an edge. The locus of center of largest empty circle passing through only 3 points in P defines a cell. The Voronoi region of a point is unbounded if and only if the point is a vertex of the convex hull. Let us see how. This is the duality. These sides which are outside and sharing the half infinite edges, these are the half infinite edges. So all these sides are the sharing half infinite edges. So these edges, these sides can be connected to each other and they will result in a convex hull like this. There is another duality, that is, if we can connect all the Voronoi sides, then it will result in a Delaunay triangulation, which is another very good concept of nearest neighbor problem. We can use the Voronoi diagrams for following, for searching the nearest neighbor, as we seen, for constructing closest pair of points, for finding the largest empty circle, for computing Euclidean minimum spanning tree. So the applications will have the Euclidean nearest neighbor searching problem, that is finding the nearest neighboring points, the Euclidean or nearest neighbor problem, and another things are used in the data clustering and pattern recognitions. It can be used for the simulation of polycrystalline structure with Voronoi diagrams. So, for our particular reason, our particular problem, that is nearest hospital problem, we can use the Voronoi diagram efficiently. Thank you. So, we have seen that all this can be done for the nearest hospital problem using the Voronoi diagram.